Hello. Today we're going to talk about the first part of what we call experimental design. And in this lesson, we're going to be able to differentiate between an observational study and an experiment. You'll also be able to, and we're going to recognize and use some vocabulary that will relate to experimental designs. And then we're going to define and apply principles of an experimental design, and then be able to differentiate between forms of control in an experiment. First of all, knowing what's the difference between an observational studies versus experiments. Well, the first thing, an observational studies is basically what it says. It is there is no treatment assigned. You basically, researchers merely observe a characteristic in the subjects, and we usually say it's done either as prospective or retrospective. And so prospective just basically means you pick the subjects, then you follow them and observe their behavior over some time. Retrospective doesn't mean you're going to pick your subjects, but you're going to go back and look at information, previous records like medical records, observe their behavior that way. Experiments on an observational, we're looking or we're observing, but in an experiments, or also known as experimental studies, there is actually a treatment. Okay, they are assigned. Okay, you don't choose what treatment you get, you are assigned a treatment, and hopefully this is done randomly. And that the researchers observe the response and measure the effect of the treatments. So the big difference is observational, there is no treatment assigned, and in an experiment, there isn't a treatment and they are assigned, and hopefully they're done randomly. Okay, so here's just some example. It says the journal Circulation reported that among 1,900 people who had heart attacks, those who drank an average of 19 cups of tea a week were 44% more likely than non-drinkers to survive at least 3 years after the attack. Observational or experiment? The best way to answer this was there any treatment? No, there wasn't. So this is an observation. Because the people they got to choose whether they wanted to drink a lot of tea or not drink a lot of tea. And they were not randomly assigned to drink tea or not. Okay, so observational study or experiment? Well, the fact that they went and looked at 13 years of medical records is a good indicator that this is an observational study. People in the study were not randomly assigned to live close or far from the broadcast antennas. And it's definitely retrospective because it says it looked at 13 years of medical records. Well, the fact that they're randomly assigned, the fact that they are given a treatment, which is the diet, then we would say that this is an experiment. The people in the study were randomly assigned, and they were each given a specific meals. Why do we do experiments? Well, we do experiments because it's the only way that we can show a cause and effect is with a randomized experiment. Random assignment of a subject to treatment. In observational experiments, there exists what we call lurking variables, okay? And lurking variables are things that are out there, and since we didn't give any treatment, we're not really sure that what we're observing had an effect on the results, but it's because of those lurking variables, and it's not the variable we're studying. All right, so this is some vocabulary that you need to know when you talk about an experimental design. So the first thing you have is your experimental unit, which is also known as what we call the subject, okay? And this subject is some single individual person or animal or plant or whatever it is to which these treatments are going to be assigned to them, okay? Because remember, we said experiments have treatments. And so your explanatory variable is also oftentimes referred to as the treatment, the specific experimental condition that's going to be applied to that subject. Now, a factor is a variable that is being tested. And then level is what we refer to the specific options for a factor. Now, treatments are made up of factors and at different levels, okay? Now, when it's just one factor, that's pretty straightforward, but sometimes it can get tricky because there can be multiple factors. are being tested with one experiment. The last thing we need, which is a response variable. And a response variable is what is it that you're measuring at the end of the experiment after the treatments have been applied. And when you talk about response variables, when you talk about your subjects, when you talk about your factors and your levels and your treatments, it's always important that you are specific. Put everything in context when you are talking about it. Okay, so let's look at, here's an example. A farm product manufacturer wants to determine if a yield of crop is different when the soil is treated with 3 different types of fertilizer. 15 similar plots of land are planted with the same type of seed, but are fertilized differently. So at the end of the growing season, the mean yield from the sample plots is compared. So in this case, what is my experimental unit? What is my subject? Okay. And in this case, that's going to be the plots of land. Well, what are you doing with these plots of land? You're going to give them a type of fertilizer. Are there different levels of Are there different levels of fertilizer? And yes, we have, it says there are 3 different types. Now I'm going to call them, and many times you'll be given specific names or whatever, but I'm going to call them fertilizers type A, B, and C. How many treatments are there? Well, there's one factor with 3 different levels. So basically there's going to be 3 different treatments. And then my response variable is the yield of your crop. Okay. Does one give you a better yield than the other? It says a consumer group wants to test cake pans to see which works best and bakes evenly. It will test the aluminum, the glass, and the silicone pans in both gas and electric ovens. Sorry. Okay, what is it that I'm actually going to use is going to be my subject. Well, I'm testing cake pans, so obviously I'm going to have cake batter. And then what are my factors? Okay, well, it says here I'm going to test them in different types of pans, and I'm also going to use different types of ovens. So I actually have several factors here, or at least 2. I have 2 factors. I have the type of pan I'm going to use, and I'm going to have the type of oven, okay? Well, my levels are in the type of pan. It says I'm going to use aluminum, a glass, and a silicone pan. So that's 3 different levels in the type of pan. And in my gas and in my oven, I'm using 2 different types. I'm using a gas or electric. So in my levels, I have 3 levels of the types of pan: aluminum, glass, and silicone. And then in my ovens, I have 2 types, 2 levels, which is electric and gas. So if you think about it, 3 levels. I have basically 2 factors: the aluminum done in both the oven and the electric and the gas, the glass done in both the electric and the gas, and the silicone done in both the electric and the gas. So ultimately that makes it 6 treatments. And then when all said and done, what is it that I'm looking at? Well, which one bakes the pan more evenly? So the big picture is that our main goal is to conduct an experiment to collect evidence for a cause and effect relationship between the explanatory and the response variable. And in order to accomplish this, we have to follow 4 basic principles. And of course, the very first one is that a well-designed experiment is going to include a comparison, which means that you have to use at least 2 treatment groups so that you have something to compare against. Why is comparison important? Well, it's the results that we are getting statistically significant. So it gives us a baseline for comparing the effects of other treatments. And then, of course, the second thing you have is randomization, is the chance to assign a subject and units to treatments. And well, why is this important? Equalizes all your other variables. So remember when we talked about there might be some lurking variables out of there. Well, when you use randomization, then you kind of equalize all those variables and gives treatment groups that are more or less the same, okay? And then we have replication, okay? Replication is using multiple subjects in each treatment group, and if possible, repeating that experiment multiple times with different groups of subjects. And of course, why is this important? You want to make sure that what we get isn't a fluke. You want to replicate it because if you replicate it many times, it gives a better idea about the amount of variability within each treatment group. And the last thing is control, okay? So the importance of control is because it makes conditions similar as possible for all treatment groups, aside from the actual treatment, of course. Why is it important? That you're minimizing the effects of other variables on our response variable. So we want to make sure that there aren't other things out there making that could be affecting your response variable. We can observe the difference between what we want to be able to say is the difference because of the treatments and not something else. So you that's the point of a control. Some examples of some ways to make them better, okay? So these extras tie in with one or more of the four necessary components of experiments, which we said was comparison, randomization, replication, and control. So the first thing here is an example of a study on stomach ulcers, okay? And in 1958, an initial experiment of a very creative treatment of stomach ulcers, which involved, number one, anesthetizing the patient, basically putting them out, putting a balloon in the patient's stomach, and then filling the balloon with this freezing coolant, which apparently was supposed to freeze the ulcers or whatever. And in this initial experiment, all 24 patients, all were cured. Treatment became very popular, even more so than surgery, but there were some skeptics. And so you have to ask yourself, what do you think is wrong with this experiment? Okay, now think about what we say are the four components: comparison, randomization, control, and replication. Well, there was only one kind of treatment. So what are they comparing it to? So let's talk about control group, which is very important when you're doing an experimental design. A control group is a group that is used to compare the factor against, okay? And a control group, like I said, could be, think of it as a starting place or a base level. And oftentimes, so let's go back to this experiment, And they did a new experiment in 1963. And so they had a controlled experiment was performed. So basically, a group of 160 ulcer patients were divided into two groups, and the groups were random. 82 of them received the gastric freezing treatment, and they found that 34% were improved. And we're assuming that this is randomly assigned as far as that goes. And 78 received a placebo treatment, and that gastro freezing basically was no better than a placebo. So this is starts you to question, okay? So let's talk about control group. Now, to note, though this is called a control group, it really ties in with comparison, like I said earlier. And if there's only one treatment we're testing, we have to have a control group in order to have that crucial element of comparison. And also, if two or more treatments we're comparing, a control group could still be a good idea, okay? Because the different treatments or the different drugs that you're trying, is that making a difference if you're only comparing it between each other? But if you compare it to a control versus not getting it, you have a better sense of how effective or beneficial it could have, if there is any benefit whatsoever. So control groups are very important, and it is a type of comparison. So, like we said, the control group would either receive no treatment, or maybe a previous version of a treatment, or placebo. And I'm sure you've all heard of the placebo. Okay. A placebo is basically a fake treatment that has no true physical effect on the response variable. Okay. A new medication, then your placebo could be one, like I said, it's a pill that looks, or maybe it's an injection. It's the same, looks the same, feels the same. Everything is the same, except that the placebo has no true physical effect on the response variable. But you want your subjects to get the same treatment as far as having to take a pill or get a shot or whatever. But sometimes when you do this, we have what is called the placebo effect. And the best way I like to think of this, and I know I'm dating myself, but there used to be a show called MASH. I'm sure some of you are familiar with it. And there was a scene or an episode in MASH. They were a mobile hospital, and they were performing surgeries, and they ran out of pain medicine. Oh, it begins with an M. Anyway, they had this pain medication, and they were completely out of it. Okay. Morphine. Thank you. That's what it was. And they didn't know what to do, and because it was treating pain. So basically what they decided to do was just basically have the patients think that they were injecting them with a needle or giving them a pill or whatever it was, so that they would think that they were getting the pain medicine. And what they noticed was the patients, like the minute they got it, they were like, oh, thank you, I just feel so much better. When in reality, they didn't get it. And that's what is kind of referred to as the placebo effect. Okay. It's a phenomenon where we see changing in the response variable is seen with any treatment, so that even when a subject is not getting the real thing, they think they are, and that somehow enough. Okay. But if your real treatment doesn't work any better than the fake one, was your treatment all that good? And actually not really. Okay. If getting the fake is giving the same results as giving the real one, then you have to wonder whether or not it's even real, even with the placebo effect. Okay, so let's look at another way of control is what we call blinding. Okay, and blinding basically says that the subject doesn't know which treatment they are getting. Okay, and why would you want to do that? Well, think about that. Like I said, when they were getting the pain medication, if they knew they were just getting sugar pills or just getting water injections, would they have liked that? No. So blinding, if you don't know what you're getting, then you don't have that flawed by the fact of knowing you got the real one versus getting a placebo. Okay, double blind is when not only does the subject not know what treatment they're getting, but those that are administering it or have any contact with you, the evaluator, they don't know which treatment each subject is receiving. If the doctor or the nurse knows what type of treatment you're getting and knows that you got the placebo and you say, I feel better, they may question, no, you don't. Because they know that you got that. So therefore, sometimes double blind, neither the subjects nor the evaluators know which treatments each subject has received. Okay. But the evaluator, once again, could mean whoever checks the subject for improvement, but is also includes the person who administers the treatment or cares for the subject during the experiment, basically anyone that has direct contact with the subject. Now, you may say, well, if they're double blinded, how do they know who's getting what? There is somebody somewhere that knows who's getting what. It's just those that are in direct contact with the subject don't know what you're getting. So blinding is a control method. Okay. It helps make all treatment groups the same. If no one knows what the treatments they're receiving and takes away some of that variability or that bias, the response variable might occur if the subjects and or the evaluator know who's getting what treatment. So that's why blinding and double blinded are important. Okay, so here's just some examples. A pharmaceutical company is testing a new headache medicine pill and wishes to test it in an experimental study against a control group. So, is it possible for the experiment to be blinded or double blinded? I would say probably yes. Okay. If you're trying a headache medicine, if you know you're getting the real thing versus just, once again, a sugar pill, if you don't know what you're getting, then it has a better chance of the results having more validity or not. Okay. And so when you have a control group, when you know the ones that didn't get the treatment and then those that did get the treatment, so when you're comparing it, if those that didn't get the treatment versus those that did, and there was a vast improvement on those that did get it, well, then you can say that this treatment was significantly statistically significant compared to a control group. And that's the whole point of a control group, is something, some baseline, something to compare it to. Okay, here's another one. There's a cutting-edge treatment for fighting brain tumors, which involves drilling tiny holes in the patient's skull and injecting a drug cocktail into the brain. Possible for an experiment to be blinded or double-blinded? I suppose it would, but I would question the ethicalness of drilling a hole in somebody's brain and not really doing anything to it, but just to subject them to the same treatment. So is it ethical? Probably not. Okay, there's an SAT prep class, okay? And they have 20 students, and they break them into two groups. The first group are kids that care about their grades, so they choose to take the SAT prep class. And then there's group B, the kids that don't care about their grades, so they don't take the SAT prep class. And so then, group A scores way higher. It worked, okay? They're saying the SAT prep. Well, what's wrong with this? Think about it. Okay, sorry. Let's go back here. The question that becomes, what's wrong with it, is this is making the assumption that because they took the SAT prep class, that group A, they were kids that cared about their grades and they took the SAT prep class and they did way better. So it's because they took the SAT prep class. Well, the problem is when you look at what group A is, these were kids that cared about their grades and they chose to take this SAT prep class. But their motivation to do well was created long before they took this SAT prep class. And the kids in group B, they didn't care. So if they didn't care about their grades, they don't take the prep class. And not that they couldn't do well, but they didn't have the motivation to want to. So the question becomes, is it the SAT prep class that caused these kids to do well? Or could it be something else? Could it be the fact that they are conscious about their grades and they probably study very well and work very hard at it? So this is what we call confounding, all right? And confounding is that two variables are confounded when they both have a connection with the response variable. So in other words, on that SAT prep class, you don't know, is it because the kids care about their grades and are probably very studious, or is it because they took the SAT prep class? So when you can't always tell if it's the confounding variable or the explanatory variable, or could it be both that is actually responsible for the change in the response variable? So we refer to this, you may see this term, they call it lurking variables. Confounding and lurking variables are very, very similar concepts. And we tend to use lurking when we're talking about observational, and we tend to use confounding when we are talking about an experiment. However, just so you know, on an AP exam, you're never expected to differentiate between the two. But so confounding and lurking are pretty much similar. So the whole point, let's put myself over here. The whole point of randomly assigned treatments is to help minimize the effects of confounding variables. But if there's a specific variable that we know of and are concerned about, there is a way for us to control that variable. And that is what we call blocking. It's a form of control. So blocking could just be something that you know has an effect on something. And so you want to make sure, keep moving myself around here. We're going to separate subjects into groups with similar characteristics. Okay, so we're going to block what that confounding variable could be, but just by the fact that we're going to put them all in similar characteristic groups. Okay, this characteristic could be based on a variable that we truly do believe has some effect on the response variable. It could be the age. It could be gender. It could be uh, age, gender, what color. There's lots of things that it could be out there. And in many cases, when you're looking at it, they'll tell you things that they know will have an effect on something, so you know that you need to block it. It's a form of control. Excuse me. And then once you've blocked it, then you go and randomly assign the treatments within each block. Okay. So, what do you think about blocking? Think about it. Why did we do, when we were doing sampling, we talked about stratifying samples? Well, why did we do that? We went and wanted to make sure that we had representation from each type of group, and so we stratified it. So blocking is kind of is what we do in experiments. As we stratifying is what we do to sampling. Okay. Once again, blocking and stratifying are similar concepts. The difference is really just about context. We use stratify when we're describing a random sample, taking a random sample, and we use block when we describe an experimental design. And so that's all we're going to do today. The next lesson is going to talk about how to make a completely randomized experiment, and also how to do it with blocking. So have a great evening.